Hi, everybody. How are we doing today? We are moving along in Algebra 1. We are now in Unit 2. We've been talking about functions and how we're slowly starting to progress to define these things more. We were dealing with equations. We realized that there are some equations that are very specific. They have certain attributes, like none of their x's in the domain repeat. And that gives them a classification that we like to call a function. And then from there, it keeps progressing from that. We can keep getting more and more specific as we start to define these more and more. So today we're really going to start talking about defining these types of functions via their graphs, via table of values, and by actual equations, and start to think we can start thinking more in depth about this and use this information to help us gather more information about these particular functions. First off, let's start to look at graphs. We've talked slightly in the past about this, but look, graphs can be three different types of ways. We could have a continuous graph. Notice they have attributes here. The line, there isn't a line, and it's a nice smooth line, continuous line from one side all the way over to the other. Sometimes they go on forever, like this one. Sometimes they're restricted values, but the line of the graph itself is a smooth, continuous line. So things to look for, smooth lines. Domains on these. Your domain is going to be a range of x values. Usually we write this with inequalities. So, for example, this one is all real numbers, or it's from negative infinity to positive infinity. We know this because we can look, see the arrows. It says it goes on forever and ever on both sides. But of course, sometimes we could have restrictions. Another type of graph. This is easy to get away. Look how these look so totally different. Uh, this is a graph full of dots. These dots are coordinates, and they mean specific things to the graph. No other point on this graph makes sense. So this is why discrete graphs are only used dots. And we'll talk more about that. Remember, this is something that could be like a model that function. This function models like going to the store and buying, let's say, basketballs. But you're never going to go to a sporting goods store and buy a half a basketball. Only the balls, like right on the measures. 1, 2, 3 makes sense. In this case, you never know because we have points on both the negative and positive side of the x-axis. But whatever this is, say if this is like -2, and this is -1, and this is 1, and this is 2, and this is 3. These points make specific sense according to the graph. There's no real description to this, but that's kind of like, what we're talking about here. We have to interpret graphs and information depending on what they give us. In this case, these are individual dots. Our domain, when we go to write a domain like this, our domain would be a set of numbers, that are only the x coordinates of each one of these points. So it'd be the set of, let's say, -2, -1, 1, 2, and 3. That would be the domain of this. Individual numbers in a set. It's all the x coordinates of these particular points. Of course, the other end of it is that it's neither of them. Notice that this graph has a break in it. That means it's not continuous. It's continuous for a little bit and then it stops. And then it's continuous again over here, but it is not fully continuous to the whole graph. It's not a graph of just dots, so it's not just discrete. It's somewhere in between. All right, so that means that it is neither discrete nor continuous. Let's see our examples and see how this starts to go. They want us to look at this particular graph and say, okay, is this graph continuous or discrete? So if you put your pencil on one side and you start to trace the value over, it is a nice smooth line. We can go even farther than this. If they asked us, let's say, to define this graph, and they're saying this graph is representing a bird that drops a stick and the stick slowly falls down to the ground. And I will say, what is the domain of this graph? Well, we know that it starts here. This is when the bird first drops it. So that's 0, right? And which is less than x. which is less than, and we need to know, well, when does it hit the ground? So it's 1, 2, 3, 4, 5, 6. And there you go. Those are the only x values that are being used. So our x values are in between 0 and 6. That's how you represent that. This one here, they want to know is, okay, and of course, it's, I'm going to just write a C, it's continuous. This one here, again, the dots give it away. This is a discrete graph. And again, if we were to sit here and we're going to say, well, what would the domain of this graph look like? Well, this domain, and here is like a set notation, right? Well, that's really not a pretty set notation. Best we can do when you're writing with a mouse. Right? Set notation. There we go. I would say if you look at this, right, the x coordinate here would be a -2, a -1. If 0 is being used, 1 would be used, and 2 would be used. Separate variances with a comma, and it is in the brackets that represent a solution set. So again, discrete graph, and we're looking at a domain of just a bunch of x values, the x values that are being used for this particular problem. Not too bad, right? Pretty easy when we're looking at graphs to be able to say, hey, I know that this is discrete. I know this is continuous from a graph. That's the picture. We also can start to look at some of these here, right? Getting even more specific than the function just being discrete or continuous. We can now also start to think, is this graph linear or nonlinear? Are these functions linear or nonlinear? Are they continuous linear? Are they discrete linear? We're adding to our knowledge here, and we start to think about these. So this is the first thing you have to do. First off, when you're looking at comparing tables of values, okay, your x's must have some sort of even change going on, that you're able, or at least enough of an even change that you can prove or predict that this, what's going to happen. You always have to look at the x's first. Look, our x is here. When you have a horizontal style table of values, the top one is usually your x, the bottom one is your y. So you look 2010, 2012, 2014, 2016, and these represent years. Your wages are represented by your y's. It's like kind of how much money you're making over time. Notice these are going by even increments. So yes, we check this first box. We are good to go here. And then we can take the difference of our y's to determine if it's linear. If the difference is the same every single time, you know you are following a slope that is constant in this. So you should, if you graph these points, you're going to get a line. So let's start to see what happens when we do this. So again, here we go. We're going to take this one, and you subtract it from your first one. And we look at, okay, that difference is 2.5. K, because we're dealing with thousands. Then we need to do the next one. So same thing here. We're going to take your one ahead of it, 25 minus 22.5. And we look, and what do we get? 2.5. Okay, great. Do the third one. Just make sure. Do it every single one. 27.5 minus 25,000. What do we get? Real quick math. Oh, yeah, here we go. Right? Did everybody get that? 2.5. So you have a change of 2.5 from here to here. You have a change of 2.5 from here to here. You have a change of 2.5 from here to here. It's growing. Every time your x increases by 2, your y's are going up by 2.5 thousand. So yes, is this linear? This is definitely a linear function. And you're able to go from there. We don't know much else content to this, but there you go. You can see, is your x's changing by an even increment? Yes. Then you can take the difference in your y's, and you find out that every single time it changes at a constant rate, that is indicative of a linear function. So we're able to start getting even more defined. Look at our next example. Here's somebody who's filling a swimming pool. right? And let's say they fill the swimming pool. They know that the pool is full after 30 hours of being filled. It should be completely full. They want us to know a couple of things here. We need to, is this graph discrete, continuous? They want to know, well, how much water does the pool actually hold? So, I mean, we could actually use function notation here. They also want to know what is, let's see, a G of 30. Remember we did that last class? Function notation, evaluate this function. We can evaluate it simply knowing if we can prove that this is linear, we can easily evaluate it. If we can't, well, then that's kind of useless. Is it continuous? Is it not continuous? We got to think of all these things. So first, let's see, are we even dealing with a linear function? So we look at our x's. Notice our x's are changing by a nice constant value of 5. After 5 hours, there's 60 gallons. After 10 hours, there's 120 gallons. 15 hours, so and so and so and so and so on. So here we go. We're going to take what? 120. We're going to minus 60. What do we get? 60. And we're going to take 180. We're going to subtract the 120. And we get 60 again. This is looking good. We'll take 240, subtract 180. We're doing that back and forth thing, so finding the difference of our y's. We also got 60. I could keep going, but I can already kind of see what's happening here, right? 300 minus 240. It's also 60. So we have a constant rate of change. We know that this is linear. Now, is it continuous or is it discrete? So what we do here in a table of values is you want to look at numbers in between what they stated. If it's discrete, only the coordinates they give you are going to make sense. If it's continuous, then we have more coordinates that aren't showing up. Does the in-between numbers make sense? So you look over here, like, for example, 6 hours. Is there water in the pool after 6 hours? What about 7 hours, 8 hours, 9 hours? Yeah, I mean, that hose isn't suddenly dumping 60 gallons of water in at once. It's gradually filling this pool up. So in 5 hours, there's 60. It's coming out of the hose at a constant rate. So yeah, this would definitely be considered a continuous graph. And what can we do to find G of 30? Well, hey, look, we can figure out, well, what is the rate changing? The rate is changing by 60 every 5 increments. So from 25 to 30 is another 5 increments. So if you take 300 and you add 60 more to it, we get G of 30 is 360 gallons. So that pool holds 360 gallons, right? Interesting how these work. We can get a lot of information that we can pull out of this when we use common sense. Think of a hot air balloon ride, right? We know what a hot air balloon is. It's a basket attached to a big balloon. They pull a chain, gas fires off, the hot air gets captured by the balloon, and up it goes because hot air rises. So this one, maybe at first we don't see this. Like, oh, wait, Mr. C, these are not in an even increment from 0 to 10. That's not 5, but everything else is going up by 5. That's okay. We have enough information in this that we can be able to come up with this. Yeah, I know this one here and doesn't quite. This is a jump of 10, and then every other one is a jump of 5. We have enough information to determine if this is actually linear or not. It makes sense that if the balloon is sitting on the ground, if it hasn't left yet, its elevation is 0. Then they're saying like 10 minutes into the flight, it's now at an elevation of, let's say, 20 feet, 15 minutes feet. We can check this. Yeah, we have enough information. We don't need this. This one here kind of like, you can like toss it aside, but we can look at the rest. This is even, this is even, this is even. Okay, we do what? 25 minus 20. We get a 5. Then we do what? 28 minus 25. And we're getting 3. We have 32 minus 28. And we get 4. Then we have 28 minus 32. And we're getting a negative 4. So look, it's kind of like it's gone up and then it slows down, but it's still going up, and it goes up another 4, and then it starts to come back down. I mean, think about it in a hot air balloon, right? What goes up must come down. So it's on its path up, and then it slowly gets to its top point and it's starting to come back down. So yeah, this makes sense, but look at the change. This change is not constant. This is nonlinear. Nonlinear. It's a nonlinear function here. But is it continuous or is it discrete? So we need to look at this as the numbers in between. If the at 0, it takes off and then it keeps going, right? Is it actually keep going and make any sense? It may be. You guys try to figure this. I want you to think about it for a second and see if you can get this. All right, did you guys come up with it? I hope so. Let's take a look. It should, if a hot air balloon is going up, it doesn't automatically stop. A few minutes into the flight, 4 minutes into the flight, it's still going up. 10 minutes into the flight, it's here. 11 minutes into the flight, you hope that it doesn't just fall out of the sky. That would not be a hot air balloon trip I wanted to be on. So I would say this is a continuous flight. All right, we look at our next table of values to determine if this is a function that is linear or nonlinear. You're selling cans of cat food. You buy no cans, it costs you no money. You buy one can, it costs you $3.27. And this is still saying in between. Looking at if it's linear or constant or discrete, is this continuous? Is this discrete? I don't know. Can you buy a half a can of cat food from Walmart? I don't think they want to sell you a half a can. Of course, I mean, you could always try and open it up and take half the can out, but I think somebody might get a little mad at the store. So notice this time, these in-between values do not make any sense. So this would be considered a discrete graph. Now, what we have to see is, though it's discrete, is this linear? Notice our change in x's, they're all fine. And if we want to go through and we want to do some subtraction here, because we need to subtract the two values, right? We take 650 or 654 minus 327. And what do we end up with? 327. Right, let's say we keep going. So we're going to take this one and subtract this one. We take 981 and we subtract 654. What do we end up with? 328. Yeah, look, so you can tell a can of cat food is $3.28. So if you add 328 to this, oh, we get that. Take this, add 328. Oh, look, we get that. So we can prove, yes, this is discrete and it's linear. And if they ask you, hey, what's the 6th can of cat? You could keep predicting this over and over and over. You can now have enough information because it's kind of like, you know, there's a pattern here. It has a constant rate of change. You can keep predicting can after can after can if you want. But remember, no store is going to let you open up that can and only buy a half a can. So that's why this is a discrete graph. Common sense helps us get through this. Another way we can take all this knowledge and figure it out is determining like linear or nonlinear just from the equation. So we have to be very careful here. Remember that in order for an equation to be linear, you cannot have a negative exponent, which of course, remember, I'm going to show this real quick. A negative exponent, like negative, we'll just say 1 raised to the negative 1 power. Remember our exponent laws from pre-algebra says that if you have this, the negative exponent rule says you take the reciprocal and the power becomes negative. Or sorry, the power becomes positive. So take the reciprocal, and now that -1 becomes a positive 1. So that's 1 over x. So x to the -2 power. Take the reciprocal, and the power becomes positive. So 1 over x squared. So notice it forces the x, a negative exponent forces your x into the denominator. So in order for an equation to be linear, it cannot be raised to any negative exponent, which also means that if you see a x in a denominator of a fraction in this equation, it is not linear. Also, any exponent that x is raised to, it cannot be greater than 1 or it can't be less than 1, which means you can't have x raised to the 1/2 power, right? X cannot be raised to a 1/2 power. That's actually the square root of x. So both of those are true. You can't have x's in radicals. You can't have x to the 1/2 power. And of course, you can't have x to any power other than 1, which means you can't have an x squared, an x cubed, an x to the 5th power, and so on. So let's start to look at these and see, does it match any of this? So example 5, is this a linear equation? Well, look where our x is. I see that my x is in a denominator, right? If you wanted to be fancy, we wanted to rewrite this. This could also look like this. Y is equal to x to the -1 plus 2 power. That is not linear. Definitely not linear. Here's one super easy for us to tell. All right, look, right here. It's raised to a power of 2 or 3. Here, if you use the power to power rule, then you'd have it also raised to another power other than 1. This is not linear because we have powers that are greater than 1. Ooh, they used function notation this time. So instead of a y, we have the fancy y, the function notation, f of x. So here's function f, where its independent variable is an x. Notice, where's our x? Our x is in a numerator of a fraction. That's perfectly legal. In fact, if we wanted to rewrite this, make it maybe something we can see from our past, from our pre-algebra days, going to turn the f of x to y is equal to, I'm going to break this fraction up, 1/2 x plus 1. Wow, that's slope-intercept form, right? Y equals mx plus b. Oh, perfectly legal. Absolutely, this is linear. Our x is in the numerator of a fraction, totally fine. It is technically being raised to the power of 1. Good to go. That is linear. And again, this one too, if you look at this last one, this is as classic as it gets. Y equals mx plus b. Your slope is 12. Your x is being raised to the power 1. This too is also a linear equation. So that is it for this lesson, guys. Hopefully you're figuring out that with some common sense, thinking about these problems, we can go through, we can see that there's many ways we can represent functions, whether it be an actual equation, a table, graphs, and we can start to even get more detailed in our description of these, being able to say, hey, is it continuous? Is it discrete? Now we're starting to learn, is it continuous, discrete? Is it linear? Is it nonlinear? Okay, and we can keep going from there. Get out there, do that homework, and have a wonderful day, guys.